Howdy everyone, Generative here. Welcome to another episode of 6 Minutes Paper Talk podcast, where we dive into the latest research in AI, radar signal processing, and more. Today, we're discussing a fascinating paper titled Physics-Aware Generative Adversarial Networks for Radar-Based Human Activity Recognition. These are the authors. This is Professor Gurbuz from the University of Alabama, and this is Professor Amin from the Villanova University in Pennsylvania. Let's start by framing the problem this paper addresses. Traditional GANs, or generative adversarial networks, have been used to synthesize RF microdoppler signatures to train deep neural networks for human activity recognition. However, these GANs often produce kinematic inconsistencies, leading to decreased performance. Why? Because GANs, as in a legacy perspective, they come from the natural images. And we are not talking about natural images here, we're talking about microdoppler signature images, which is a frequency time representation of a time series. So this paper is basically introduces what the industry now call physics-aware machine learning by employing two methods, and we will dive into it very soon. Now, in the introduction section, the authors highlights all of the widespread use of short-range radars in applications like security, smart environments, human-computer interface, and the focus is on microdoppler signatures, which are crucial for classifying human activities. They point out the limited and unbalanced data available for training deep learning models that necessitates the synthesis of more representative data. Now, unlike natural images, when a person sees a cat, anyone can say this is a cat and basically label the image. In radars, the images look completely different. You can see here some frequency time images or spectrograms, and to the naked eye, it doesn't mean anything. You have to be well aware of what is microdoppler and well aware of the theory to understand what's going on here. And it doesn't mean anything to a usual data labeler type of human. So it's hard to label radar data. And so we augment it by, for example, generating synthetic data using GANs. Okay, what is physics-aware GAN, or physics-aware machine learning? This concept combines physics-based models with data-driven deep learning. This paper discusses how physics machine learning leverages domain knowledge for electromagnetic backscatter studies, while also benefiting from deep learning's ability to capture sensor-specific properties. The authors propose integrating physics-based constraints into GAN to improve synthetic data quality. In this page, they are describing the single and dual envelope MB-GAN. We'll discuss that. They have some kinematic error examples here that GANs without physics were generated, like disjoint components, an additional component here, and so on. And they have here the upper and lower envelope extraction from different thresholds. They extract the envelope of these images, and they use it as an auxiliary branch, as a physical constraint, so to speak, or physical information, how this signature should look like. Okay, this is the auxiliary branch that they introduce here. This is just one introduction, or just one addition to the usual branch of the GANs. They do the same for the upper envelope and lower envelope, and they do testing on both and just one. Okay, the data collection, they use a TI AWR 1642 radar in an indoor lab. It's positioned 1.5 meters above the ground, and 14 different human activities were recorded. The activities included various gates, daily tasks, each repeated multiple times by participants of different age, different physical profile, so a diversity of participants. And here you can see the neural network that they propose. You can see that the envelope is in the auxiliary. You can see the relevant activation functions they use. Okay? And this section is introducing what they, basically the innovation of the paper, except for the auxiliary branch there. They introduce a term in the loss function that basically penalizes the loss function if it doesn't comply or adhere to a physics-based term. And they evaluated what is the best physics term out of three options. Well, the one is the dynamic time warping distance, the other one is discrete Frechet distance, and the third one they evaluated is MSE, if I'm not mistaken. Yeah, Euclidean distance, yes, L2 norm. And then they choose, I think, to use the dynamic time warping distance, and they continue with the performance training, and they conclude that this kind of physics-aware neural network is best performing with this addition to the loss function, this term to the loss function, the physics-based term, and the multi-branch GAN is performing the best. Thank you for joining me on this deep dive into the world of physics-aware GANs for radar human activity recognition. As always, if you find this discussion insightful, please like, please subscribe, and please share this episode with someone who might benefit from it. And as always, your feedback is really, really valuable to me, so let me know in the comments what you want me to discuss next, how can I improve the content to better serve your interest. Thanks again for listening, and I'll see you in the next episode. Regev out.